Welcome to Study Loop.
Here we have there's a box resting on a table and then another box hanging from a string over a pulley here. So I've drawn free body diagrams of these. Technically this one is kind of down here. So here, this is the box that is free to move horizontally, and this is the one that's free to move vertically, and here's our pulley. So we have a weight and a tension in the pulley. That tension is also in this side of the string or the rope that's going around the pulley. Because the pulley has inertia, this tension is not necessarily the same as this tension. But this tension is the same as this tension because that's in the same part of the rope. And then that tension is applied to this. And so positive, I'm going to say to the right for this block, down for this one, and counterclockwise for the pulley. Have a friction force acting on here, and then these are reaction forces at the center of the pulley. We're told that this one block weighs 12 kilograms, this one, the one hanging, weighs 5, the pulley weighs 2, and the pulley has a radius of 0.25 meters. And I guess they tell us that it's a frictionless surface, so friction force is 0, so we don't have to worry about that. So looking at this body here, we have, and if this is positive, we have minus T1 plus WT equals M2A. And we're told that this, the belt around here, or the rope, is not slipping on this pulley. So we know that the angular acceleration of the pulley equals the acceleration of this block divided by R. And we also know that that acceleration of this block must be the vertical acceleration of this block must be the horizontal acceleration of that block. Let's see here. Looking at this block in the horizontal direction, we just have T2 equals M1A because the friction force is 0. The pulley is assumed to be a uniform cylinder, so its moment of inertia is 1/2 M2R squared. And a moment balance on this about the center here is T1R minus T2R equals J, the mass moment times the angular acceleration. Now, we can do a bunch of, basically we need to eliminate things. We can take this and plug it in here, take this, solve for T1, plug it in here, solve for T2, plug it in here, make the weight M2G, use this relationship here and here, and we get an equation that we can then solve for A. And I didn't go through all the algebra here, but in the end, A comes out to be M2G all over the quantity 1/2 M3 plus M2 plus M1. So we can see here that, let's see here, say M1 and M2, say M1 is 0 and M3 is 0. So this is 0 and this is 0. Then this cancels, this goes away, and then A is just G because then this is just free falling. So that makes sense. If M2 is 0, then A is 0 because if there's no weight down here, then there's nothing to pull, getting this to start moving. Anyway, and we can see that, as M1 and M2 increase, then A goes down. So in this case, when we plug in our values, we get 2.72 meters per second squared. Once we have that, we can plug back into here. Knowing the weight, we get that the tension in this part of the vertical part of the cable is 32.6 newtons. And then we can plug this into here, and we get the tension in the horizontal part of the cable is 35.4 newtons. So you can see that they are different because if this were 0, so J, if this was massless, and this was 0, then they'd have to be equal. But because we have mass in the pulley and it's accelerating, there's a net torque on the pulley. Now, they also asked us for the reaction forces in the pulley. And so if we just do force balance in the pulley's center of mass isn't accelerating, so Rx must equal T2. And Ry must equal T1 plus the weight of the pulley, and that's 55 newtons.